This short video is an introduction to MO theory. It's hopefully a bit of a refresher for you. We're just going to go over some of the main points which were covered in Chem 101.1. What we want to use MO theory for is to be able to quickly and reasonably accurately predict electronic energy levels for molecules. So we'll develop MO a bit more in the lecture beyond what's in this video. The main thing we're going to be building towards is being able to identify HOMO and LUMO. So these are highest occupied molecular orbitals and lowest unoccupied molecular orbitals. And we'll have a look at how conjugation particularly affects the relative energies of HOMO and LUMO orbitals. And then we'll relate that to the optical transitions that are available to certain molecules. We've drawn a lot of these Jablonski style diagrams with electronic energy levels indicated as horizontal lines. We've labelled them S0, S1, S2, S3, and so on so far. The S, of course, indicating the singlet spin. Often you see it drawn with extra information about the energy levels, such as their sigma star antibonding or their N orbitals for non-bonding. And the transitions between them are indicated as a pi-pi star transition, for example. So we're interested in just understanding what these labels mean and what the implications are for the transitions. Furthermore, we want to be able to predict what transitions are available in a given molecule. So we'll have some idea of what its photophysics is going to be. So the way to find out what all the allowed energies of a system are, and therefore what transitions are available to it, is to solve the Schrödinger equation. If you remember, this equation takes the wave functions of all the atoms that go into a molecule, works out how they interact, and then determines what the allowed wave functions for the electrons once you've made the molecule are. The full solution gives you a full description. You get the electronic, vibrational, and rotational energy levels. This is the hard way to do it, even with the computational power that we have available to us today. It's still a case where approximations need to be made, and as you go to very large molecules, those approximations get greater and greater. Molecular orbital theory provides a reasonably straightforward and certainly much more convenient way to get an overall idea of a molecule's energy levels without having to do all of the calculations involved in solving the Schrödinger equation. One approximation it does make that's worth being aware of is that it considers electronic variables only. So the rearrangement of electron density is all that's involved. Now, the main idea behind MO theory is that it takes the atomic orbitals available from the atoms involved in making the molecule and mixes them into molecular orbitals. Now, these molecular orbitals are similar to the atomic orbitals that we're familiar with, in that you can put up to 2 electrons in a molecular orbital, and they need to be spin paired if they're both occupying the same orbital. We think of the orbital as a volume of space. What it is it's the volume of space where, if you want to think in terms of particles, that's where the electron is most likely to be found, or if you think in terms of waves, that's where most of the amplitude of that electron wave is found. The outer contour of the molecular orbital, just like for an atomic orbital, is defined at some point, whether it's 90 or 95 or 99%. Typically, they're drawn at 95%. So this slide shows how that's done. It's the simplest case. We've got two hydrogen atoms. The atomic orbitals involved are 1s, and there's one electron in each of those. These atomic orbitals interact constructively and destructively. When they interact constructively, we get a bonding orbital. Here's the bonding MO. And when they interact destructively, we get the antibonding MO. The notation for the antibonding is this little asterisk. The constructive overlap, to give the bonding molecular orbital, lowers the overall energy. So that's the energy drop. So that's a stabilizing process. And so when the electrons, so we start off with an electron here, we've got an electron there. When they overlap, they end up having to spin pair, and they're in here. Those electrons are lower in energy, the whole system is stabilized, and that's why hydrogen molecules form. The energy of the antibonding orbital is the same energy, but it's now increased. So that's positive, that's negative. Now that's an important point. This process of going from atomic orbitals to molecular orbitals can't create or destroy energy. So the total energy stabilization of bonding orbitals has to match the energy destabilization of antibonding orbitals. Also, you can't create and destroy orbitals. So the same number of molecular orbitals must be present at the end as the number of atomic orbitals that you started with. So you can see here we've got 2 atomic orbitals, we end up with 2 molecular orbitals. Now the shape of the bonding MO is this ellipsoid shape. That I think is reasonably intuitive. If you put the electrons there in between the 2 hydrogen nuclei, they get stabilized. The antibonding molecular orbital has an interesting shape, and if you remember, it's got one of these things called the nodal plane, and that nodal plane just means that there is 0 electron density. Or if you like, there's 0 probability of finding the electron there. But that's where the particle way of thinking about it breaks down a bit, because how does the electron get from one side of the plane to the other if it can never be in the plane? Better to think of it as a wave in that instance. Right, so we'll skip through these reasonably quickly. This hopefully should be quite familiar to you. You can also get end-on overlap to create molecular orbitals with sigma symmetry by overlapping p orbitals. The p orbitals that point in the same direction as each other can overlap like this to give you a bonding orbital. Out of phase end-on overlap gives you an antibonding orbital. Now these pictures over here on the right are actual calculations. So this is what the calculated molecular orbitals look like. This is solving the Schrödinger equation for the overlap of 2 end-on 2p atomic orbitals. You can see there's an area of lots of amplitude here between the nuclei, and then there are lobes either side. This is pretty close to the simple picture drawn here. Likewise, the overlap, the out-of-phase overlap for the antibonding orbital gives you these smaller lobes in between the nuclei and larger lobes on the other sides of the nuclei, and that's pretty similar to what's calculated. So the surfaces of these red and blue volumes will be, say, the 95% contour. And these shapes trace out the volume of space where you have 95% of the electron. When you say the electron's in that molecular orbital, you mean it's in that volume of space 95% of the time, or that 95% of its amplitude is in that volume of space at any point in time. Now, you can also overlap p atomic orbitals in a side-on fashion. And when you do this, down here you get two regions of constructive overlap happening when it's in-phase overlap. And this leads to a bonding orbital. But if you look closely, you can see that if you rotate around the internuclear axis, it's not going to look the same as it rotates around. It's not symmetrical around the internuclear axis because it has these two lobes separated by a nodal plane. So that's unlike the molecular orbitals that you get from overlap of s atomic orbitals or end-on overlap of p atomic orbitals. So that's why we give them the label pi, because that symmetry is different. So the sigma designation means they're symmetrical around the internuclear axis. Pi means they're not. And if we overlap side-on but out of phase, like up here, we actually end up with a molecular orbital that has 4 lobes and 2 nodal planes. And that's the antibonding orbital from side-on overlap, the pi star orbital. Now, of course, the energy that the bonding orbital has been decreased by is the same as the energy that the anti-bonding orbital has been increased by. So that's the same as for end-on overlap as well. So let's put this into practice. And the example that's always brought out to show why MO theory works better than other models such as valence bond theory or even simple Lewis electron dot diagrams is taking 2 oxygen atoms and making molecular oxygen. So the first step is to have a look at the atomic orbitals involved and work out what molecular orbitals these will lead to. So here are the atomic orbitals for 2 oxygen atoms. Each atom has a 2s orbital with 2 electrons in it. It has 2 p orbitals with 4 electrons in them. Another little approximation to be aware of here is that the 1s orbitals are so much lower in energy. They're core electrons. They don't play a role in forming the molecular orbitals. The second step is to look at the electrons and then work out how they will be distributed across the MOs once you've made them. Okay, so let's do this. Let's make an oxygen molecule. So first of all, we need to mix the 2s atomic orbitals and make a pair of molecular orbitals. One is lower energy, that's going to be a sigma bonding orbital. The other is higher energy, that's a sigma star antibonding orbital. Then we overlap the end-on p orbitals. We get another sigma bonding orbital and another sigma star. What is this silly line that keeps appearing? Keep rubbing that out. Sigma star antibonding orbital. Then we take the p orbitals and overlap them side on. Now there's going to be 2 sets with the same energy. So that'll give us a pair of, this line is very annoying, a pair of pi it's not pi star, a pair of pi orbitals that are bonding and a pair of pi orbitals that are anti-bonding. Okay. Now, we've got our orbitals. We need to work out which ones are filled, half filled, or vacant. So we start at the bottom and up we go. Now it's worth noting, if you remember, that was sigma, that was sigma star, that was sigma. It's perfectly okay to put electrons into an anti-bonding orbital. If that anti-bonding orbital is low enough energy, then that's fine. So it's labelled anti-bonding because that's with respect to the atomic orbitals that it came from. But this sigma anti-bonding orbital here is still lower energy than any of the molecular orbitals in this set up here, made from the 2p atomic orbitals. So it fills up with electrons first. We simply fill just going up in increasing energy. We've put 6 electrons in. We have a total of 12 to place, so we keep going. We can put 4 in these pi bonding orbitals here. There's still 2 electrons to go. We have to obey Hund's rule because these pi anti-bonding orbitals are the same energy. We put 1 in each and we align their spins. So we treat molecular orbitals in the same way as atomic orbitals. When they are degenerate, when they have the same energy, we singly fill them first and align the spins of the electrons. Okay, this is looking good. We now have a prediction. And the prediction is that molecular oxygen has 2 unpaired electrons in its ground state. That's these 2 up here. What this means is that the ground state has triplet spin, not singlet spin, because these guys have to have aligned spins. It has a T0 ground state. A couple of things to check when you've done your molecular orbital diagrams to help make sure that they're correct is just check that the number of orbitals and number of electrons are consistent. So we started with 8 atomic orbitals and we ended up with 8 molecular orbitals. We had 12 electrons in our atomic orbitals, we have 12 electrons across the molecular orbitals. Now we can go and do the experiment. We can do some science and investigate the ground state of molecular oxygen. 2 unpaired electrons in the ground state means that molecular oxygen is paramagnetic and should respond to a magnetic field. So you can get liquid oxygen by cooling down air. Liquid nitrogen has a slightly lower boiling point, so by using liquid nitrogen you can actually cool down air and get some liquid oxygen. Now you may have seen this done in a first year lecture. So once you have your beaker of liquid oxygen, it's very cold, so of course you'll need to handle it with very thick insulating gloves. You can tip it into a magnetic field. Tip it into the space between 2 powerful magnets and the liquid oxygen will actually stay suspended in that volume of space between the 2 magnets. It's a pretty cool demonstration. It's very direct and it proves that molecular oxygen is paramagnetic, and that's something that's predicted by molecular orbital theory. It takes just a minute or 2 to construct that molecular orbital diagram and come to that conclusion. Now, something else that you may not have noticed in the liquid oxygen demonstration in first year is that if you have a nice full beaker of liquid oxygen, it can have a little bit of a blue tinge to it. And where this comes from is a very neat little piece of photophysics, which I'll just tell you about to finish off this movie. That transition from the ground state, from the T0 state, up to the first excited state, involves moving an electron from the pi star orbitals up to a sigma star orbital. And that's a transition that requires a photon of about 1260 nanometers, which is in the near infrared. However, in the liquid state, molecules are close enough together so that two oxygen molecules can transiently interact and form what you might call an oxygen tetramer, or a dimer of dimers. So it looks a little bit like this. Here's an oxygen molecule. Here's another oxygen molecule, and they can interact and form this little tetramer, oxygen tetramer. It's transient and it requires a high concentration to form, hence the liquid state is required. But what can happen is that both the molecules in this tetramer can simultaneously undergo excitation with a photon of twice the energy. So one photon at 630 nanometers can excite a transition which would normally require a 1260 nanometer photon, provided it happens for both molecules at the same time. Now, of course, 630 nanometers is red. So that means a beaker full of liquid oxygen absorbs a little bit of red light and looks blue.